Hello, everybody. This is Mr. Arnold coming live from the Arnold Plantation. Uh, Today we're going to talk about a little bit of chemistry. I know you guys have been excited to talk about chemistry for so long. It's been 3 weeks since we've really got a chance to talk. So we're going to start a new chapter. This chapter is called Organic Chemistry. It is what people cry about when they're in college. They call it OChem. They probably call it some other initial chems too, but it is not that bad. We're just going to brush the surface of this. We're not going to be so deep into this that it gives you nightmares or anything, but we're going to find out what it is, and we're also going to learn how to name some compounds. So let's just get started. All right, so organic chemistry, right? Covalently bonded carbons. That's the main thing. Covalently bonded carbons. And that's what the basis of organic chemistry is, at least the definition that we know as of right now. It didn't used to be the same as it is now. It used to mean coming from life, right? And because when they first started studying organic chemistry, everything that was carbon compounds, they came from life. They were something that was alive that made that, or it grew, and that's what the study began. But after they developed chemistry a little bit more over time, they learned they could synthesize or make their own organic compounds from things that weren't alive. So the coming from life definition no longer really works. Okay, the best way to look at this is, let's see what the organic gardener thinks, right? Because if you're an organic gardener, everything you use is all natural, right? It has to be special. It has to make sure there's no chemicals in it. There's no artificial fertilizers, no artificial plastics or anything like that being used. Everything's all natural. Well, for the organic chemist, that is the farthest from the truth, because the study of these covalently bonded carbons includes, I have to change the size of this font a little bit, includes, plastics, right? The most dreaded thing of all organic purists, gardenists, is using plastics and artificial fertilizers and oil and all those gases and all that kind of stuff. Those are all organic compounds, and that's what we're really going to look at as the shape of these carbons and how we can change them and make them what we are. So the organic chemist is going to say that it's just going to be the covalently bonded carbons, and it's going to include all these unnatural things that didn't exist before humans started to manipulate the carbon compounds. All right, so let's get started on this thing. All right, now the reason carbon is so important, and it has its own branch of chemistry, is because there are more carbon compounds than all the other elements compounds combined. They can do all sorts of different things that most elements can't do. They can form, and I share this on the site here, they can form chains. And what I mean by a chain is just what it sounds like. My little picture on the site here, it's a big long chain of carbon compounds, right? They can form rings, right? And right here, this is called a benzene ring. It's a very common ring in chemistry, something that you'll get to know a little bit better in a second. Also, when you have these chains, they can have like branches. So it's not just a straight compound. It has these little teeny branches, and they can be branches all sorts of different places. And these last three we already know, right? We know that carbon can form single bonds, double bonds, and triple bonds. not every element can do that. Remember, carbon has 4 valence electrons, which means it has the most open spots and the most bonding sites of any element. So that's why carbon's so unique. All right, so let's look at this other thing here. So we have some things that are important for us, and one of those is isomers, right? And here's another reason there's so many carbon compounds, because you can have this same exact compound, same exact formula, but the shape can be different. All right, so let's look at this. We're going to do some counting, some higher mathematical skills here. We're going to count. If we look at this little molecule on the left, we have 1, 2, 3, 4, 5, 6 carbons. Jot that down so I don't forget. 6, right? And we also have, and I'm going to change colors, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 hydrogens. So we have 12 hydrogens. Okay. Now, when we look at that molecule beside that, I think I used light blue, didn't I? Let's count those carbons again. 1, 2, 3, 4, 5, 6. 6 carbons. What a coinkydink. And then we go to count our hydrogens. Oh my gosh, I wonder what it's going to be. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Oh my goodness gracious. The same exact formula, but a different structure. That's what an isomer is. And there's all sorts of different isomers around there, right? And there's also things that you think are isomers until you really look at them, and they're not. So we're going to go over here to the side. Now look at this here. I drew these out just to save you guys time, right? We have 5 carbons in each, right? And so you're thinking, oh yeah, that's an isomer, right? 5 carbons. Now look, I didn't draw hydrogens on here, and this is something that you'll get used to in a little bit. We're not going to draw all the hydrogens. It just takes too long. Just like class, right? So when we go through and we count those, we see that, oh yeah, we have the same number of carbons. We have the same number of hydrogens. So that you think that's an isomer. Well, it's not. It's not an isomer because it's the same exact molecule. The only difference is this, it's like a rope. This rope is laying in a straight line, right? And if you have a rope and you coil it up, and you coil up as many times as you want, even tie it in a knot, it's still the same rope. So it's not different. It's the same thing. It's just laying a different way. And that's what this compound here is showing. All right? Now, we'll look at this one over here. Now, I drew that because it matches that first compound over there on the left. See that? You look at that same thing. Oh yeah, look, now the double bond's on the other side. Is that an isomer? And you know how tricky Mr. Arnold is. Of course that's not an isomer because it's the same exact molecule. We're just like seeing it on the other side. It'd be like if you were behind it and you could look at it, right? In class I would normally show you this, but I can't do that because I don't have a thin piece of paper or a video that will show that. I can just flip it around. So, but it's the same molecule because it's just laying. It's like if you're seeing it from the opposite side. All right. We have some other isomers down here, and you can count those up, and you're going to see that they're the same numbers, right? So you can do that. I won't bother you with that. You just do that. You fill those numbers in, and you look here, and you see, oh, Mr. Arnold at it again, because that one and that one are not isomers, but they're the same exact structure. They're just one is flipped upside down. All right. Any questions with that? If you have questions, you can email me and ask me. If you're not sure what I'm talking about at all, we can have a chit chat on the telephone, or we can text each other for an hour and a half and try to figure this thing out. But remember the rule. If it seems too difficult and it's confusing, you're thinking way too hard. It's as simple as it sounds. Same formula, same number of carbons and hydrogens, different structure. Moving on. Okay, now, also with these carbon things, things we have to worry about is the properties, right? The properties of these isomers are going to be different because it's going to change the shape. It's going to make them act different. Now look at these two here, right? They're the same weight, everything like that's the same, but they don't melt at the same point. They don't boil at the same point. They behave similar, but not exactly the same. It changes, and the main thing that changes most of the time would be the polarity, right? Look at this thing. If it's a perfect circle, it's not going to be polar. There's nothing that's different on any side. But if you look at this other one, it has that double bond right there. And that's going to change it. So the electronegativity on one side, the charges on one side are going to be a little bit different. There's 2 hydrogens over here on this side, and there's 3 on the other side. So it's going to change the way it is because of that double bond. And so a lot of compounds change their characteristics because of their shape. And it has to do mostly with being polar and nonpolar. Having a bond that's different. Having something added on to it on one side or the other, making it different, making it a little stickier, like we like to say, right? The opposites attract. I'm doing my finger thing right now with my water, just in case you wanted to know. You know I'm doing that. But we look at these things. Now, I'm going to draw on here so we can see again. I drew an alcohol right here. This is called ethanol. And ethanol is what they use like as a gasoline additive. And it's 2 carbons. And there's hydrogens on these. I didn't draw them on there because, you know, we don't like to draw. They get sloppy if you have to draw all those hydrogens on there. But there are hydrogens there, right? And those hydrogens on there. And then there's this thing right here, right? An OH. Now, in the past, you see that OH and you're thinking, oh my gosh, that's a base. No. If it were a base, it'd have to be ionically bonded. But in this case, it's covalently bonded. And we don't call that hydroxide like we did in the acid-base section. Instead, we're going to give it this cool name, and I'm not spelling this wrong, hydroxyl. Right? And the difference between hydroxide and hydroxyl, they're still the same thing, is this is on an organic compound. It's covalently bonded. All right, back to the point. So we have that O on this side, right? So that's going to make this thing polar. It's going to be polar because it's going to have one side that's positive, one side that's negative. So it's going to stick to other water. It's going to stick to water molecules. It's going to stick to other alcohol molecules. It's polar. So remember, likes dissolve likes. Alcohol dissolves in water. Now, we said it was a gasoline additive, right? We have octane here. Now, octane is not the only chemical that's in gasoline. Gasoline has hundreds of different chemicals, but octane is what they have on the pump. They say 97% octane rating. That's the old way. It just tells how well it burns, but octane is a compound that would be in gasoline, all right? And so these have similar evaporation amount rates and boiling points. They're both liquids at room temperature, but they evaporate really fast, right? And look at the size of this thing. It has 8 carbons, so 12 times 8, 96 weight of carbon. Plus it has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. 18 hydrogens, which weigh 1 each. So it weighs 114 grams per 1 mole. Right? That's pretty big. You look at the alcohol, it's 12 times 2, which is 24, plus an oxygen, which weighs 16, and then 1, 2, 3, 4, 5, 6 hydrogens. And so that's my stomach growling there. And this is a 6, and that weighs 46, right? Compare. This is over twice as big, right? So it should, since it's bigger, be harder to evaporate, right? The bigger it is, the harder it is to get to move. This is small, so it should evaporate easier. But the reason they're not that much difference is because of that polarness of the alcohol. It makes it stick together more, right? Alcohol is not near as polar as what water would be, right? And water only weighs 18, right? And water is much harder to make evaporate than the ethanol, the alcohol, or the octane, right? Or the gasoline. I hope that makes sense. Okay, I'm going to go back over here to these things. So when we say polar versus nonpolar, right? If it's polar, let's put yellow there. And if it's nonpolar, we'll put red over here. I'm just going to use arrows. If it's polar, that boiling point will be higher, right? It's harder to make it boil. The nonpolar, it'll be lower, right? They evaporate, they boil easier. Melting point, it's sticking together more, right? So melting point. So to make it melt, it's sticking together, so it'll be harder to melt, right? So the melting point will be higher for the polar. And the one that was nonpolar, the octane, it'll have a lower melting point, right? Because it's not sticking together. So you have to get it colder and colder and colder. I'm talking about freezing right now, but the melting and freezing point are the same. You get to get it colder and colder, which means lower energy to make it stick together. And the same thing through densities, right? So if it's denser, because it's held closer together, this would have a higher density. And this would have lower. And we know this one from water and oil, right? Oil's much, much bigger molecule than water is. But the water molecules are held close together, tight together because of their polarity. They're polar, they're going to stick together. Pulling them tighter makes them denser. All right, I hope that helps. All right, now let's go back to some other things. Now here's another type of isomer. We're not going to spend a lot of time with this isomer here, but this is on the shape. Geometric isomers, geometry, shapes, right? And this one is talking about something we're called cis and trans. Now, when we say cis means they're on the same side. Oops, I have it written right down here below it, so I'm not going to rewrite it. I'm just going to highlight it. So cis says same side, right? And then let's look. Right? Those CLs are on the same side. That is cis. Trans, right? Trans means the opposite side. So if you look at this, it's shaped like that. So even the shape of the molecule, where they're located, will change their properties. Again, this would have to do with polar and nonpolar, right? You have negatives right here. Right here, they're spread out a little bit different, so it's going to change. It's going to change their attractions to other things just by their shape or where those chlorines are at in this case. All right, now, if you haven't realized this yet, our regular formulas aren't going to do us much good, right? We use like H2O and CO2, right? That's because in those compounds, there's pretty much only one shape they're going to be in. They're going to be the shape they are. But now we start looking at these carbon compounds with all these different isomers. We're going to have the same formulas in different shapes and different properties. So we need a different way to name. We need to be able to name things in a different way so that people know exactly what molecule it is. And so we're going to have to use structural formulas, which would be, our dash model. I always call it the dot and the dash. So we're going to use these kind of models. And we did this earlier this year, and we'll come back. And by the time you get done with this chapter, you'll be an expert at that kind of structure. All right, well, I think I already passed my time. I was only going to go like 10 minutes. What we'll do is we'll stop right here for today. And all I'm asking you to do is homework-wise is fill out these notes the way I'm filling them out. And if you fill these notes out with me, there's added worksheets that are with them, we'll count those as your points. And we'll, for today's points, if you have the notes done up till the section 2, where I'm at there, we will give you credit for that. And as we get going through these notes, if you haven't looked through, there are pages of problems and naming things. It's the only way I know how to show you how to do it is to just do it. That's the easiest way. So, and we'll decide on different point things, and I'll say, okay, this is worth this much point as we go through the list. All right, I hope you guys are all being safe out there and practicing social distancing and being careful. Have a good day and keep up with your work. All right, goodbye.